Salam sejahtera and good day to Dr. Sakina and our classmates. We are from Group Pretzel and today we will be presenting our project about modeling wolf and deer population using Lotka Volterra. Our group members are Nur Arniza binti Aliman, Nur Akila binti Sulaiman, myself Ramya Kathiresan and Shantini Murthy. As an introduction, I would like to start by explaining Lotka Volterra model. It is the simplest model of predator-prey interactions, and the model was developed independently by Lotka in 1925 and Volterra 1926. The equations in Lotka-Volterra model can be written simply as a system of first-order nonlinear ordinary differential equations. Some of the assumptions that were made in this Lotka-Volterra model are: number one, prey population finds ample food at all times. Number two, the food supply at the predator population depends entirely on the size of the prey population. Number three, the rate of change of population is proportional to its size. Number four, during the process, the environment does not change in favor of one species. And number five, predators have limitless appetite. The general equations in the Lotka-Volterra model can be written as dx over dt equals alpha x minus beta xy, which represents the prey population, which is deer population. And the second equation is dy over dt equals delta xy minus gamma y, which is the predator population or the wolf population. Since we know that the two populations can be in equilibrium with one another, we can solve the Lotka-Volterra equations to determine when this occurs. And in equilibrium means that the population are not changing with respect to time. The system of equations can be written as 0 equals alpha x minus beta xy and 0 equals delta xy minus gamma y. We then solve the equations for solutions of x and y, giving us the following solutions, which are the first one, x equals 0 and y equals 0, and the second one, x equals alpha over beta and y equals gamma over delta. The first solution shows that if both populations are extinct, then they will continue to be extinct until an outside factor can change that. The second solution describes an equilibrium where the population of the prey is equal to the ratio of the constants, alpha and beta, and the population of the predator is a ratio of delta and gamma. For our problem statement, we start by modifying the equations. In our project, we will examine the two species that are intertwined in predator-prey relationship, which is the population of deer and wolf, same as the initial one in Lotka-Volterra model, which is the population of lynx and snowshoe hare. From the study, the theory has predicted that following a rise of prey, then the population of predator also increases and vice versa. To exhibit this behavior, we can develop a Lotka-Volterra model for wolf and deer population as well. From the original equation, we have modified by adding a new variable and changed the factors of the equation. Firstly, we let xt be the population of deer and yt be the population of wolf. Focusing on xt, the prey population, we assume Malthusian growth, which means the population grows in proportion to its own population. And we represent it as a1xt. As mentioned before, in this modified equation, we add a new factor as well, a2xt, where it is the death of the deer due to starvation. And the last one is the death of the deer due to predation by wolf, which is modeled by a negative term, negative a3xtwt. Therefore, the growth model for the deer population is dxt over dt equals a1xt minus a2xt minus a3xtyt. For the wolf population, we only change the factor without adding or removing them. b2ytxt is the primary growth for the wolf population and depends on sufficient food for raising wolf cub. It implies an adequate nutrient from predation on deer. The wolf population declines due to hunters and implies the negative term, negative b1yt. Thus, the growth model for wolf population is dyt over dt equals negative b1yt plus b2yt xt. The next part is we identify the equations. Both the equations are ordinary differential equations and they are in first order, non-linear, non-homogeneous, and they have variable coefficients. For our project, we have chosen this dataset and we have used it to solve the model. The data has been collected from the year 1998 to 2007. The next part is equilibrium analysis. In equilibrium analysis, there are 2 points where the system of equations in a Lotka-Volterra model becomes at equilibrium. And those points are extinction equilibrium and coexistence equilibrium. Assuming x represents deer population and y represents wolf population, the model equation of deer and wolf with the function of t is shown as stated. The extinction equilibrium occurs when there is no population of deer and wolf left in the environment. Therefore, the population of deer and wolf will be 0. So the extinction equilibrium point is x naught y naught equals 0, 0. For coexistence equilibrium, the coexistence equilibrium occurs when the population of the deer and the population of wolf in the environment are equal. At this point, the population rate of deer and wolf becomes 0, which means dx over dt equals 0 and dy over dt equals 0. When dx over dt equals 0, the equation becomes a1x minus a2x minus a3xy equals 0. And when we solve it, we obtain x equals 0 and y equals a1 minus a2 over a3. For dy over dt equals 0, the equation becomes negative b1y plus b2xy equals 0. And when we solve it, we obtain y equals 0, x equals b1 over b2. From these values, it can be concluded that the coexistence equilibrium occurs when x equals b1 over b2 and when y equals a1 minus a2 over a3. So the coexistence equilibrium point is XE, YE equals B1 over B2, A1 minus A2 over A3. The next part is assuming parameters. A1, A2, B1, and B2, which are the parameter values for the interaction between deer and wolf, were obtained using a piece of information written in an ecological modeling journal. A2 was calculated using the information provided in the chosen dataset. This is because A2 is a variable that was added to the equation during the modifying equation process. The calculation for A2 is done as stated. Because given in the dataset that the initial values are x0 equals 2000, y0 equals 10, and the deer population change dx over dt equals 300 during year 1998. Therefore, we obtain the value of A2, which is 0.85. For problem solving, we start by linearization analysis at equilibrium points. As the equations in the system are nonlinear, the equations are linearized using Jacobian matrix first in order to solve the ODE equations. Noted that fxy equals dx over dt equals a1x minus a2x minus a3xy, and gxy equals dy over dt equals negative b1y plus b2xy. So the linearized equations are d over dt matrix xy equals Jacobian x minus x star y minus y star, which are the points where the equations are linearized. Thus, the linearized equations at point x star y star are matrix dx over dt dy over dt equals matrix a1 minus a2 minus a3y minus a3x b2y minus b1 plus b2x multiplied by the matrix x minus x star and y minus y star. The linearization analysis at extinction equilibriums gives us dx over dt equals 0.65x and dy over dt equals negative 0.25y. For coexistence equilibrium, we obtain dx over dt equals 13 over 2.4 times 10 power 6 minus 1 over 2.4 times 10 power 6y, and dy over dt equals 3.9 times 10 power 5x minus 7500. Before proceeding to the solution, x is named y1 and y is named y2 to ease the calculation process. Therefore, dx over dt equals dy1 over dt equals y1 prime. dy over dt equals dy2 over dt equals y2 prime.
Okay, so I'll continue to explain about finding the eigenvalues and eigenvectors. So before this, now we have the equation y1 prime equals to negative 1 over 2.4 times 10 to the power of 6 y2 plus 13 over 2.4 times 10 to the power of 6, and the y2 prime is equals to 3.9 times 10 to the power of y1, and then minus 7,500. So if you write it in the matrix form, we have matrix A, which is 0, 3.9 times 10 to the power of 5, and then negative 1 over 2.4 times 10 to the power of 6, then 0. So if you simplify the negative 1 over 2.4 times 10 to the power of 6, you'll get negative 4.167 times 10 to the power of negative 7. So the next process is we should be doing A minus lambda, then identity matrix. So after doing the process, we got a value as shown here. Then we will have to proceed to the characteristic polynomial process. And then the characteristic polynomial process, after doing the AD minus BC format, we will be getting lambda squared plus 0.1625. So solving the characteristic equation, we'll get lambda 1 equals to 0.403i and lambda 2 equals to negative 0.403i. I stands for negative square root 1, square root of negative 1, which is a complex number. So now we have obtained eigenvalues that are complex. So to find the eigenvector, the process is similar as finding the eigenvector from the values as how we do for the real numbers. We just have to multiply it by the x1 and x2, then we will get the results 0 and 0. So if you use the row 1, we will get the equation negative 0.403 ix1 minus 4.167 times 10 to the power of negative 7 x2 is equals to 0. So if we simplify the equation, we will get x2 equals to negative 967,122.63 I x1. Here, as the eigenvalue obtained is a complex number. So now, after this, we will be proceeding to the solution process. But as our eigenvalues are complex, we will have to continue with another process. Eigenvector for value 1, the lambda 1, will be 1 and 967,122.63i. Okay, next. And then for the second one will be the similar, but the negative will be converted into a positive number. So we have two eigenvectors over here. One is 1 negative 967,122.63i. Another one is 1 967,122.63i. The first one occurs when the lambda 1 is 0.403i, and second one occurs when the lambda 2 is negative 0.403i. And now we will be proceeding to the general solution. Usually for this equation, we will have to write the general equation as y equals to c1 e to the power of lambda 1 t, then eigenvector 1 plus c2 e lambda 2 t eigenvector 2. So if you write this equation, then in final we will be having y1 equals to c1 e to the power of 0.403 it plus c2 e negative 0.403 it. And for y2 we'll be having in a similar way, but the constant will be changed into negative 967,122.63 I. We are having two equations right now, which are known to be the general solution, but that contains complex eigenvalues. In order to eliminate the complex number, a complex exponential, we will have to use Taylor's formula. So Taylor's formula is noted as e to the power of a plus I bt equals to e to the power of at times by cos bt plus I sin bt. So I have expanded the equation, using the y1 values, and finally I can get that c1 cos 0.403t plus c2 cos negative over here is 1, 2, 3, 4. In the fourth line of y1 solution, you'll be getting an expanded solution. At that expanded solution, we can take out the I and factorize it. So after we factorize it, we will be getting a certain value plus I times another certain value. So if we see here, this is similar to ut plus I dt. So we can show that u and v are two linearly independent solutions to the system of differential equations. So we can use them to form the general solution. Thus, the general solution is just that you take the value of ut and you take the value of bt and sum up together. So that becomes the general solution. And simplify as y1 equals to c1 cos 0.403t plus sine 0.403t, and then plus C2 cos negative 0.403t plus sine negative 0.403t. So here there is no eigenvalue with complex number, and our team has eliminated it. In a similar way, we will have to continue the same process for y2. So our team did in this way using Euler's formula. Here a point to note is we have multiplied 967,122.63i. I is another complex number. So when we multiply this into that, one of the I becomes I square, another one stays as I. The I square value is negative 1 because when we multiply or square square of negative 1, we will be getting negative 1. So we multiply the value negative 1 in the position of I square. So in a similar way, we can conclude that this equation can be written in the form of ut plus ibt. We can show that u and v are two linearly independent solutions to the system of differential equation. So we can use them to form the general solution again as in the process of y1. Simplified equation, we will be getting 967,122.63 times the whole in the bracket c1 cos 0.40t plus sine 0.40t plus C2 cos negative 0.40t minus sine negative 0.40. Okay, now we have to note that x is named y1 and y is named y2 to ease the calculation process initially. So now we have to substitute back the x and y values. So we will have the equation for xt equals to an equation and yt equals to another equation. Okay, now this is our general solution. To find the specific solution, we have to substitute the initial values. So in the initial value that given in our data is x0 equals to 2000 and y0 equals to 10 when the time is 0. So after substituting this equation, I'll be getting two simultaneous equations. One is C2 equals to 2000 minus C1, and another one is C1 minus C2 is equals to 1.034 times 10 to the power of negative 5. So substituting the equation number 1 into the number 2, we will be getting C1 equals to 1000 and C2 equals to 1000. So then our team simplified the solution. So this is the final solution for the Lotka Volterra model system of interaction between deer and wolf that our team has modified. So after finding the solution for x and y, now we have to go for the phase portrait. So phase portrait is done for the x in equilibrium. Initially, we didn't do finding the eigenvalues and vectors for the extinction equilibrium. This is because during the extinction equilibrium, the rate of change of population of deer and wolf will be equals to 0. So at that position, we cannot create any equation. So we used the equation in equilibrium in order to find eigenvalues, eigenvectors, and finally the solutions of x and y. In a similar way, we did the phase portrait for x and y in equilibrium. So when the x and y are equilibrium, the point is 1 over 120,000 and 13. And then our A matrix will be 0, negative 1 over 2.4 times 10 to the power of 6, 3.9 times 10 to the power of 5, and 0. So lambda 1 and lambda 2, as we know, both are complex eigenvalues. So these complex eigenvalues does not have a real part. The real part is equals to 0. So therefore, this phase portrait will look as a spiral with a center. So this is a stable center. So as shown in this diagram, the phase portrait is a stable center in anti-clockwise direction. In order to determine the direction, our team decided to look at a point which is 1, 0, then times the equation by our matrix A, and then the next point will be 0 and 3.9 times 10 to the power of 5, which means that the point will be flowing from 1, 0 to 3.9 times to the 10 to the power of 5, which is above in the y-axis. So it flows in the anti-clockwise direction, and we will be getting a phase portrait stable center in anti-clockwise direction. Okay, that is all for our assignment, and this is our project, Lotka Volterra model, which we did the modeling for deer and wolf population. Thank you.